Hello, everyone, and welcome back. In the previous few videos, we've been focusing on more advanced methods for solving definite and indefinite integration problems. I want to continue with that in this video. And what I want to focus on are slightly more obscure and more technical problems that when I show you them on the surface, they don't look like the type of integrals that you could use a lot of these techniques on. And so what I want to focus on are little tips and tricks that can bring these integrals into a form where we can start using the techniques that we've been developing over the previous few lectures and videos. So that means that what we're going to focus on today are primarily examples and classes of integrals. And I want to show you how these techniques and these little tricks can be used in the hopes that maybe when you come across a similar integral, you can remember some of these tips and tricks in order to solve that one too. So let's jump right in. The first class of integrals that I want to focus on are given like this: x over ax plus b dx. So this is a quotient of linear functions. A and b are any real numbers you want them to be. Preferably a is not going to be equal to 0. Otherwise, you're just left with x divided by a constant, which is an easy integral. Now, if you look at this, this doesn't fall into the criteria for the method of partial fractions. And it also, we can't use long division here in order to turn this into a proper integral. So the question is, what can be done? Well, I want to propose something that maybe you would do accidentally when you start this problem, and then you would realize maybe that wasn't a great idea. But what I want to do is I want to substitute for that whole denominator, ax plus b. So let me show you what happens. Ax plus b, and so I get du is equal to a dx. Okay, so I get a factor of 1 over a that comes out front from substituting for dx. My denominator turns into u, but you're going to rightfully point out to me that I still have a factor of x lying around the top. And so this probably wasn't a good substitution, or at least it looks like it wasn't a good substitution. But from my equation for u here, I know that u is equal to ax plus b. So I can rearrange this thing to see what x is equal to as a function of b, as a function of x. And so in this case, I subtract off b on both sides, divide by a, and I get this. And so what this means is that now when I put this into my integral, I have everything written in terms of u. And I still get a linear function divided by a linear function. But now I can distribute that denominator over both terms in the integral here. And I get 1 minus b u to the minus 1 du. Now, this is a very manageable integral. This looks a lot like the types of integrals that we started with way at the beginning of these lectures. And so let's go ahead and calculate this. We get u minus b ln the absolute value of u plus c. Now you can hear me say it. No one asked about u. We definitely want to back substitute for x. And so this gives me ax plus b minus b ln ax plus b. I'm trying to exaggerate those absolute values so we can see that they're there. And now let's actually distribute this thing out. So I get first the x's. So x over a, one of the factors of a is going to cancel in the top and bottom. Then the logarithmic term. And now, sorry, that's over a squared here. So maybe let's make that look a little prettier first. So that's b over a squared. And now the last term is a b over a squared again. But b over a squared is a constant. A and b are just some random numbers that we were given. So in this case, I'm just going to absorb them into the plus constant that's already on the end. I've got all my constants back there. I might as well put them all together. There is no use in putting the b over a squared in this because it disappears under the derivative. So it doesn't even matter. We're looking for the function of x here, and then we just say plus constants on the back. But with this little formula, I could then ask you to solve the following integral. So for example, I could give you this. And once we write that as a proper fraction, we can see that it is exactly in the form that I just provided up here. And in particular, a is equal to 2 and b is equal to 5. And so plugging these into our formula, we get x over 2 minus 5 over 4 natural logarithm of 2x plus 5, and then plus some constant. So isn't that a cool little trick where we showed that, sometimes you have to resolve x in terms of u when you do your substitution in order to cancel out the rest of the stuff that didn't go away with your substitution for u and du. Okay, let me show you another tricky example here. And this is going to be the class of integrals that look like this. So this will be x times the square root of ax minus b. Okay, so again, in this one, if you try to substitute for, say, ax minus b, it's still, if you try and use the same trick that I just used above, actually it's going to be a huge pain because you're going to get 1 over a fraction, and then you might have to use partial fractions. I want to show you how to do this in an even simpler way. So here's a fun little method here. So let's let u be the square root piece, ax, the square root of ax minus b, okay? And then that tells me that if I take the derivative with respect to u, I get a divided by 2 root ax minus b, right? So the a on the numerator comes from the derivative of the inner function, ax minus b, or sorry, yeah, let's do ax minus b. And the 2 comes from bringing down the power of 1/2. And there's still a dx on the end. Now, what this really tells me is that 2 over a du, 2 over a du is equal to dx over the square root of ax minus b. Okay, so that's kind of interesting, right? Because I don't think we've seen an example like this before. And what we see here is that actually the dx is doing the substitution, not the value, or not the substitution for u, because the square root, the over the square root is disappearing with the dx substitution. So I get du in here, sorry. Now, again, we have the same problem that we had for the previous example. We have still an x on the bottom. So we're going to do the same thing. We're going to use our substitution for u, and we're going to use that to find what x should be as a function of u. So if we square both sides, we get u squared is equal to ax minus b. And then if we rearrange this thing, we get x is equal to 1 over a, and then u squared plus b. Okay, so the reason I use the minus b on this is because I want the plus b here. So you'll see where this sort of comes up. But this gives me 1 over a u squared plus b. Now, multiplying that a in the denominator here into the into the denominator of the integral will cancel out those a terms. So this thing goes with this thing right here. And so now what I have left is 2 just sitting on the outside. Now what I'm going to do is I'm going to factor out a b from the entire quotient. And so this leaves me with u squared over b plus 1. And actually, I can write that a little nicer. I can write that as du over u over the square root of b all squared plus 1. And so here's where things are going to get a little crazy, because I am going to substitute again. You don't necessarily have to do this substitution, but I think it makes things a little more manageable. So I'll put it in green down here. Let's say let v equal to u over the square root of b. And then this tells me dv is equal to 1 over root b du. And so if I take 1 square root of b out of this term right here, that will leave me with a 2 over root b sitting out front. And now I have the integral of v squared plus 1 over v squared plus 1, which we should remember this one is arctangent. It's tan inverse. So this gives me 2 over root b tan inverse of v plus c. And now we can do our back substitution. First, get it in terms of u. So tan inverse of u over root b, that was the v term. And then finally, get that back in terms of x. I get tan inverse of the square. Well, since we have a lot of square roots, let's put it all under a square root. And I get ax minus b divided by b. All right. Did you think when we started that integral that you would be seeing a tan inverse in here? Honestly, I seriously didn't, right? I think that's a really, really cool, clever substitution that we can make here to get us into a pretty well-known integral, especially if you've been working on those method of partial fractions problems where you keep seeing this 1 over x squared plus 1 or something like that coming up, and you're probably getting pretty good identifying where there's a tan inverse coming through. But now again, we've got a nice little formula for ourselves. So let's try and apply it to an integral. How about if I give you dx over x times the square root of 2x minus 4? Well, in this case, I've got a is equal to 2 and b is equal to 4. And so from my previous formula, so let me flip back, let's take a look at it. I've got 2 over the square root of b. Now b is equal to 4, square root is equal to 2, 2 over 2. So that's a 1 out front. We're not even going to write that. And then tan inverse of this big, beautiful square root. So this is equal to tan inverse, because the leading number is just a 1 now, 2 over the square root of b, square root of 2x minus 4 divided by 4 plus c. If you want to, you can knock off some common factors here. I don't think it'll make it much prettier, but you essentially get x minus 2 divided by 2 under the square root after taking off a common factor of 2 from every term. But it doesn't get much prettier than that. That's the solution, tan inverse of a square root. Think about where we started, right? We were stuck for a long time just sort of doing simple polynomial integration. But look at how complex this function is that we're now left with. This is a tan inverse of the square root. It is a ridiculously complicated function here. Okay, let me give you another example of an integral that we can handle using our newly obtained methods. So x times the sine inverse of a times x. So a can be a constant in our case. So here, what we are going to do is we are going to use integration by parts. So to do integration by parts, we know that we have a function multiplied by a derivative. And so in our case, we want to get sine inverse out of this thing. I hate looking at trigonometric functions in integrals because I know that it's just going to make me make a huge headache for myself. So I'm going to substitute for that. Let's write this over here a little bit more. So I want to be able to differentiate this thing away. And that means that the other piece, v prime, is equal to x. So that tells me v is equal to x squared over 2. And u prime in this case is equal to a divided by the square root of 1 minus a squared x squared. Okay? And you'll see why I did this. Sometimes these tricks are not clear until you see somebody work the whole thing through, and then it sort of makes a little bit more sense. So bear with me if you're having trouble. Well, here now I get x squared over 2 sine inverse of ax. So this is just using integration by parts. This is u times v, and then minus. Now, an a comes down front, it's a constant. A 2 comes down front from the x squared over 2 term. And we have the integral of u prime times v. So this is x squared divided by the square root of 1 minus a squared x squared dx. And you're thinking, whoop-de-doo, right? What is the point of this? Now things look like they might even be more complicated for me. But here's what I want to do. Another substitution. And in fact, we're going to use a trigonometric substitution. So let's say x equal to 1 over a sine theta. So the 1 over a comes from the fact that I want to knock off the a squared in front of the x squared. So this is the same type of thing we saw with trigonometric substitutions. If it makes you feel better, multiply a 1 over a squared into the whole square root here. But now we get dx is equal to 1 over a cos theta. Oh, sorry. And so what we're left with here is equal to x. So we have this thing is not changing at all anymore. No more integral left here. Now we have a 1 over a coming in. Sorry, I forgot the d theta. A 1 over a comes in for the dx term. That's going to cancel off the a over, or the a that's out front, that's over the 2. So I get a nice 1/2 out front. And then I get 1 over a sine of theta squared. That's x squared. The dx gives me a cos theta. And on the bottom, I get the square root of 1 minus, sine squared. Because the 1 over a will cancel once you square that thing. Okay, let's simplify it a little bit. X squared over 2 sine inverse of ax, so that doesn't change, minus 1 over 2a squared. The a squared is coming from the substitution of x is equal to 1 over a sine theta. And the numerator here becomes cos squared. Taking the square root of that gives the absolute value of cos, but we saw with trigonometric substitution, we can always just make this, take theta between minus pi over 2 and pi over 2, so it becomes positive. You know, this is sort of what people do accidentally anyways, but that will cancel with the cosine in the numerator. So really, now I've just got the integral of sine squared. And we've seen what to do with sine squared before, right? We know that we should be taking sine squareds and using the double angle formula here. So now we get 1 over 2a squared. The integral, now we use the double angle formula, which gives us that sine squared is equal to 1/2 1 minus, so 1 minus cos of 2 theta, d theta. And there's a 1/2 that comes with this, which should be out front right here. So I will put it in front of the a squared. So I get 1 over 4 a squared here now. And now I'm in the realm where I can do this integral in a relatively straightforward manner. So I get x squared over 2 sine inverse of ax minus 1 over 4a squared times theta. That's integrating up to 1. And then plus, so the minus right here and the minus right here, those things together give me a plus. The integral of cos 2 theta is 1/2 sine 2 theta and plus c. Now what we need to do is follow what we did with trigonometric substitution and get those, get things back in terms of x. The first thing that we're going to do is we're going to get rid of sine of 2 theta using the double angle formula again. So this gives me x squared over 2 sine inverse ax, so that never changed, minus 1 over 4 a squared theta. We'll substitute that in a moment. And then, I'm sorry, I forgot to distribute this should be 1 over 8 a squared, pardon me. The 1/2 was already there, and then the 4a squared from the integral. So, but please excuse me on that one, everyone. And then plus, now 1 over 4a squared cos theta sine theta. And that is from the fact that sine of 2 theta is equal to 2 cos theta sine theta. Okay, we're moving forward. We're getting there. Let's create our triangle now. So we have a right angle triangle. Here's my angle theta. I know that, so I know sine of theta is equal to ax. That's coming from my substitution. So sine is opposite over hypotenuse. So that's ax here. The hypotenuse is 1. And so the missing side is 1 minus a squared x squared. And so that tells me that cos of theta is equal to 1 minus a squared x squared divided by 1. The hypotenuse is 1, but divided by 1, we're not going to write that. And the last piece is that we can invert the sign here in order to get that theta is sine inverse of ax. So what does this all give me? X squared over 2 sine inverse ax minus 1 over 4a squared sine inverse ax. That was the substitution back for theta, plus 1 over 4a squared. Now cos and sine in here, I get ax, and then the square root of 1 minus a squared x squared plus c. And if you want to, you can knock off a factor of a here. So let me just erase this and do it all as one step. Just because I'm running out of room, this leaves me with 1 over 4a and then an x out front. But look at the manipulations that we had to go through there, right? It was integration by parts, then trigonometric substitution, and then we had to use trigonometry to undo the trigonometric substitution, right? So we can layer these methods on top of themselves in order to find more complicated integrals, or in order to evaluate more complicated integrals. Okay, now what I want to close this with is talking about some reduction formulas. So we've actually already encountered some reduction formulas. And what these reduction formulas do is that they relate, say, some function to a power to an integral involving that same function to a lower power. Okay, so let me give you an example of this. How about if I give you tan to the power of n of x, and I ask you to differentiate this, or sorry, to integrate this thing. Okay, well, here's what we're going to do. We are going to take 2 powers out of that tan to the power of n. So we're going to assume n is greater than or equal to 2 here so that we can actually do it. And so we get tan to the power of n minus 2 of x times tan squared of x dx. And so now what we're going to do is we're going to use that trigonometric identity, the Pythagorean identity for tan squared. And now I know that you're probably saying, I always forget that identity. What is it? I always forget it too, don't worry. So here's how I remember it. Let me put this in red up in the corner. I know that cos squared of x plus sine squared of x is equal to 1. And that tells me that if I divide off by cos squared everywhere, I got 1 plus sine squared over cos squared, that's tan squared of x. And 1 over cos squared, that's secant squared of x. And so this tells me that tan squared of x is equal to secant squared of x minus 1, right? So I personally always forget that trigonometric identity, but I personally never forget that sine squared plus cos squared is equal to 1. So now I just showed you a 3-line derivation of how to get it. And so in this case, I get secant squared of x minus 1. And so now dx. Now I get, let's break that up over the difference there, n minus 2 of x secant squared of x dx minus the integral of tan to the n minus 2 of x dx. Now, the far right term here, tan to the n minus 2, is 2 powers lower than what we started with. This is a reduction, right? That's why we call these things a reduction formula. It relates tan to the power of 4 to tan to the power of 2, right? You're losing 2 powers in each process here. The other piece of this is quite nice because we have tan to the power of n minus 2, and we have secant squared, which is the derivative of tan. So if you let u equal to tan of x here, you get du is equal to secant squared of x dx. And so that first integral now becomes the integral of u to the power of n minus 2 du minus the integral of tan to the n minus 2 dx. And so I'll do this all in one step. The integral here is u to the n minus 1 over n minus 1. I'm going to substitute back for tan. So I get tan to the n minus 1 of x divided by n minus 1 minus the integral of tan to the n minus 2 of x dx. Okay. So maybe you're not that impressed. Let me show you it in action. Let's give a specific example. Because technically I didn't solve the integral, right? All I did is I got it to an integral involving a power of tan that's 2 orders lower. So let's evaluate the integral of tan to the power of 5 of x dx. Well, from our formula, so with n equal to 5, we get, so what does our formula tell us? It says that the integral of tan to the 5 of x, this is equal to 1 over 4, 1 over n minus 1, tan to the 4 of x minus the integral of tan cubed of x dx. Okay, still not solved. We still have a power of tan, but with the same formula, with n equal to 3, we get that the integral of tan cubed of x is equal to 1 over 2, 1 over n minus 1, tan squared of x minus the integral of tan of x, 2 powers lower. And we actually know the integral of tan of x. This is, if you'd like, you can turn this into sine over cosine and do a substitution for u. You can find that this is equal to ln of the absolute value of cosine plus c. So put this all together. This tells me that tan to the 5 of x, well, this is equal to, this is equal to 1 over 4 tan to the 4 of x. Now minus the integral of tan cubed, but we just found what that is. So minus 1/2 tan squared of x, and then plus ln of cos of x plus c. That's pretty cool, right? It's just, again, I use this analogy a lot, but it's the Russian dolls, right? We are slowly moving to something smaller and simpler by using these reduction formulas. And to close, I want to give you 2 more reduction formulas that you can use in your studies, and you can prove them in a relatively straightforward way. So I'm not going to prove them. I'm going to leave that up to you. I will tell you this one involving the ln of x, so taking powers of the ln. You can prove this reduction formula using integration by parts. And in fact, this gives you x times ln of x n minus 1, to the power of n. And then minus n times the integral of ln of x to the power of n minus 1. So we get the power with 1 less on the exponent here now. And this is just an integration by parts problem. It's very, very, very similar to what we saw when we just did this. Remember, we did the integral of ln of x using integration by parts. So if you want to prove this, maybe take a look at what we did for the integration of just ln of x, and then see how you can use that to prove this equality here. And the last one, we can use this one. So different powers, we saw that you can use trig identities to solve this, but we can actually do this just by extracting out some derivatives. And so you can use integration by parts again. So you get sine to the n minus 1 of x cos to the m plus 1 of x divided by m plus n, and then plus n minus 1 divided by m plus n. So this one is much more involved. It's much more technical. But again, it's a reduction of order problem on the sine component here. So you're knocking off powers of sine until you just get down to powers of cosine, or just one sine value, so that you can do a nice substitution. So this one is not as elegant, but it's still a reduction formula, right? We have 2 less powers on sine than we did before. Okay, so what we've seen today is some little tricks, some little techniques, some little tips on how to solve much more complicated integrals than potentially we've seen. And in particular, what makes these more complicated is that we've mixed and matched methods. So this is something that takes a lot of practice when it comes to integration. You need to become very fluent with the methods and know and be able to recognize when you should be applying those different methods in each of the different contexts.